Good morning, everyone. I am MD Tanrid Islam. Today at ICACT 2026, I am presenting our presentation on evaluating classical machine learning classifier for real-time intrusion detection on SmartNIC. This work is conducted under the supervision of Atikur Rahman from the Department of Mechanical and Aerospace Engineering, Missouri University of Science and Technology, USA. And let me start with the real motivation behind this study. First, let us look at the real world problem in high speed network. Modern data centers are backbone network routinely handle traffic rates exceeding 100 gigabytes per second, where packet inspection must be performed under strict latency constraints. When intrusion detection systems rely on host CPUs, the associated computational overhead can quickly lead to CPU overload, resulting in delayed or missed detection of malicious traffic. In such environments, delayed intrusion detection allows attack to complete before any effective mitigation can occur. And this shows why timely detection is critical. To address this issue, SmartNIC are introduced. And the traditional intrusion detection system process packets on host CPUs, requiring traffic to traverse the full network stack before any security decision is made. This control plan-centric design introduces processing bottlenecks under high traffic rates and strict latency constraints. Smart network interface card enables programmable data plane processing, allowing security decisions to be made directly at the network interface. And Smart NIC move processing closer to the packets. Research gap. However, most existing studies focus only on accuracy. Most intrusion detection studies evaluate models primarily based on classification accuracy, such as evaluation largely ignore whether these models can operate under the computational and resource constraint of network hardware. Consequently, many high-accuracy IDS models remain impractical for real-time deployment on smart NIC platform. And this creates a gap between research and deployment. Based on this gap, we define our problem. We consider a binary intrusion detection problem where each network flow is classified as either benign or malicious, and the detection pipeline must operate under strict real-time constraints with end-to-end interference latency below 1 millisecond. The target deployment platform provides limited compute cores and memory, requiring lightweight and hardware feasible models. Our focus is real-time feasibility, not only the accuracy. One common question is why we did not use deep learning. Deep learning models often exhibit variable interference latency due to complex architecture and dynamic execution paths. Such models typically require substantial memory and computational resource with which are constrained on smart NIC platform. Moreover, deep learning interference can be non-deterministic, making it difficult to guarantee strict real-time performance. And deterministic and the lightweight models are more suitable here. Next, I will briefly discuss the dataset used. We use the NSL-KDD dataset as standardized and well-balanced benchmark for intrusion detection research. To align with the real-time SmartNIC constraints, the multi-class level are simplified into a binary classification task, benign versus malicious. And this control setup enables a fair comparison of model while isolating the impact of hardware design choices. This dataset allowed control evaluation. This slide shows our smart NIC, our machine learning pipeline. Figure 1 illustrates the end-to-end machine learning pipeline in this work, while structure follows a standard ML workflow. Each state is designed with smart NIC deployment constraint in mind, particularly during feature selection and interference. This ensures that the pipeline remains compatible with strict latency and resource limitation. Each step is designed considering hardware constraints. Feature engineering plays an important role. Categorical features are transformed using one-hot encoding to enable efficient numerical processing by classical machine learning models. Feature correlation analysis is applied to remove redundant attributes, reducing the feature space from 41 to 35 dimensions. This reduction minimizes the computational overhead and improves interference latency under SmartNIC constraints. Reduce feature helps to reduce the latency. Now I will explain why we selected these algorithms. Decision tree is selected for its ultra-fast and deterministic interference, making it suitable for strict latency constraint on SmartNIC. Random forest provides a balanced trade-off between detection and accuracy and computational cost, offering robust performance under moderate resource constraint. K-nearest neighbor, the KNN, is included as highest accuracy baseline despite its higher interference cost, highlight the trade-off between accuracy and deployability. Model selection is driven the deployment needs. In real-time system, latency is critical. Training time reflects offline models deployment and does not impact real-time deployment. Interference latency determines whether a model can operate under strict real-time constraint. In high-speed network intrusion detection, decision must be made on per packet basis, making per sample interference latency critical. And interference time matters more than training time. This slide summarizes our experimental setup. All experiments are conducted using satisfied tenfold cross-validation to ensure class distribution, consistency across training and testing splits. Model performance is evaluated using multiple metrics, including accuracy, ROC, characteristics, and configuration metrics to avoid reliance on single performance indicator. Interference time is measured separately to access real-time feasibility under SmartNIC deployment constraints. This ensures fair and reliable evaluation. Our evaluation goes to beyond accuracy. High classification accuracy alone does not guarantee deployability in real-time system. Models intended for smart NIC deployment must be satisfy strict latency and execution stability requirements in addition to predictive performance. Therefore, this work evaluates models based on both detection, effectiveness, and real-time operational feasibility. And deployability is equally important. First, let us look at decision tree results. Decision tree achieved lowest interference latency among all evaluated models, making it suitable for strict real-time constraints. This speed advantages comes with a modest reduction in detection accuracy compared to assembled-based methods. Decision tree offers a very first interference. Next, we analyze random forest performance. Random forest provides a balanced trade-off between decision detection accuracy and interference latency. It assemble structure improves robustness while maintaining feasible per sample interference time for a smart NIC deployment. Compared to the decision tree, random forest achieve notable higher AUC with acceptable latency overhead, and it provides a good balance of speed and accuracy. Now let us observe KNN results. KNN achieves high classification accuracy on the benchmark dataset. However, it distance based interference requires comparison with multiple stored samples, resulting in high per sample interference latency. This computational cost makes KNN unsuitable for real-time deployment despite strong accuracy performance. High latency limits its real-time use. This slide compares all models. Decision tree delivers the lowest per sample latency but sacrifice robustness compared to n-assemble methods. Random forest achieves perfect detection performance while maintaining deployable latency on smart NIC class hardware. Canon, despite high accuracy, exhibit prohibitively high interference latency, making it unsuitable for real-time deployment. Based on these results, we select our final models. Random forest is selected as the final model, achieve the best balance between detection, performance, and deployable latency, maintains per sample interference latency within smart NIC hardware constraints, offer higher robustness than single tree models. Why not decision tree? Although decision tree provides ultra low latency, its lower robustness makes it less reliable under dynamic and heterogeneous traffic patterns. Why not Canon? Despite higher accuracy, per sample interface latency is prohibitively high, making it unsuitable for real-time per packet smart NIC deployable. RF here the best smart NIC constraint. Every study has some limitations. The evaluation is conducted on the NSL KDD datasets, which, while standardized, does not fully capture modern encrypted traffic patterns. The study focuses on model level feasibility and does not include deployment on physical smart NIC hardware. Hardware specific optimization are outside the scope of this work, and this point towards future improvement. Next, to conclude, I will summarize the key points. High detection accuracy alone is insufficient for real-time intrusion detection. Per sample interference latency and hardware feasibility determine deployability on smart NIC platforms. Hardware error evaluation bridge the gap between machine learning research and real world network security system. And now we are discussing about the future direction. This work established a smart NIC our machine learning baseline intrusion detection, and future work will focus on direct deployment and validation on programmable smart NIC hardware. Thank you for your time, and if you have any question, feel free to ask.